And we are live. Um, so this particular problem has been delayed a few days. I was trying to think of a more sophisticated way to do it, but at the end of the day, I am going to go with the geometric methodology. So essentially, this problem is Shen, myself, am trying to say catch a bus. Hold on one second. Let me see if I can get my face here. Yes. So let's just say I'm trying to catch a bus. And what ends up happening is I am late. Well, I could be late. Um, so the bus is only going to wait 1 minute before it leaves. And I'm only going to wait 15 minutes. And if there's no bus that shows up, well, I'm just going to leave. So the question here is in the span of 1 hour, say between 8 or 9 o'clock, let's just say the bus has an equal probability of arriving anytime, and I have an equal probability of arriving anytime during that hour. What is the probability that I will be able to catch the bus? Okay, so I'm using my wonderful Remarkable here. Which is projecting on the screen, as you can see. So this is my actual first time using the projector method here, which seems to work pretty well. So let's just go into this, shall we? Some of you may realize that this is similar to the two friends that go meet at a bar. Each friend waits, 15 minutes or 30 minutes. It's all similar. So this is a best solved with a geometric probability problem. So let me just write from 0 to 60, 0 to 60, and you'll see what I mean here a little bit. So this is Shen on this time, and this is bus arrival time. So basically what this axis is showing is that axis 0 to 60 is any time that Shen arrives between 0 and 60, all right, minutes. And the bus is any time from 0 to 60. Okay, so we draw it this way to indicate, and I'm going to shade it in terms of what possibilities there are. Okay, so first off of all, let's set some boundaries. So one way you can think about this is that if we denote Shen as the x-axis and bus as the y-axis, then we actually know that one thing is that y has to be less than x plus 15. So in other words, y is less than or equal to, I should say, less than or equal to x plus 15. Okay, so what does that mean? That means my arrival time, let's just say I arrive there at 8:30. I'm going to wait until at most 8:45. If the bus shows up at 8:46, I'm gone. I'm already gone. So the bus could show up anytime between, let's just say I arrive at 8:30. Bus could show up anytime between 8:30 and 8:45. Hence, if y is the value of when the bus will arrive, y has to be less than or equal to x plus 15. And you can draw that on this graph. So so you can denote here, let's just say this is not to scale. So you say this is 15. And then it will go what? It will go all the way to when it hits this border, which should be at 45. So yeah, so 45 plus 15, 60. Okay, so it's like this. So we have this. Okay, so here, anything less than this, I'm drawing a little arrow here. That's in the realm of possibility. Okay, what about the bus? So basically, let me write this down. Shen can wait 15 minutes. Bus can wait 1 minute, right? Bus is not going to wait around 15 minutes for me. So this is a different problem than the bar problem. Like the bar problem or the two witches meet at I don't know, some coffee shop or something. Those problems, like both parties will wait for the same amount of time. So here we don't have that, right? So it's not exactly symmetrical. So okay, so this thing what I drew is basically y is less than or equal to x plus 15. All right, so if the bus is only going to wait for me for 1 minute, so you can think of this as what? So x has to be smaller. X has to be smaller than y plus 1. Right? Think about it. So if I arrive at 8:30, let's just say the bus arrived at 8:29. Okay, great, that works. But if the bus arrives at 8:28, that's not going to work, right? So I can be smaller. So I have to be smaller than y plus 1. Or put it another way, maybe this might be better. Y has to be greater than x minus 1. Yeah, that might be better. So basically, if I arrive at 8:30, the bus has to be greater than 8:29. Okay, so if I arrive at 8:30, bus has to be greater than 8:29. With this equation, it could be all the way up to 8:45 if the bus still hasn't arrived yet. So in the past, it could be at most 1 minute off, right? So it can't be like, so if it's like, if I arrive at 8:30 and the bus arrived at 8:28, well, I've already missed a bus. Okay. So y greater than x minus 1, you can imagine this could be down here. This is a -1. So this is not even part of this whole problem, but for the sake of just drawing it, so we have here, this is +1. So this technically intersects down here. So we have a graph here that goes all the way to what? So when x is 60, this is greater than or equal. This is 59. So this is 59. Okay, so it's like right here. So okay, so this is 1. So the y-intercept here is -1. X-intercept here is 1. Here, the intersects at 60. So basically, we have here, and this is greater than. Okay, so we have this thin band over here, okay? So all solutions are within this band. So anywhere within this band, it means that either the bus arrived 1 minute before I arrived, or it's arriving within 15 minutes after my arrival. So what we want to do is find the area of this shaded area of this shaded area. All right. Hopefully you see the red dot divided by this whole entire area, Okay. So this is what I mean by geometric probability, right? So geometric probability, so total area, so shaded area divided by total area. Okay. So total area is 60 squared. All right. I was going to write 60 times 60, but whatever. 60 squared is just the area of this square. All right. Now, you could try to figure this out. It's a little complicated. I'm just going to cheat and just say, hey, look, it's just subtracting these little white triangle here and this triangle here. Both of these can go away, right? So not good. So basically you miss a bus. Not good. All right. So let's just remove the not good regions. So how do you remove that? Well, you take the total area 60 squared. Okay, this is not good. This one, you can probably tell 15. Okay, so this is 45. So this is 45, 60 to 15, right? That's 45 right here. So this area is 45. This here is naturally 45. So basically, this is a triangle. So 60, so it's 45 squared divided by 2. Then you subtract another one. Here, what do you think this is? Well, this is, we said it, this is 59. This here is 59. So this is minus 59 squared divided by 2. And that's it. So let's do the math. 60 squared minus, okay, so if you do the math, I'm not going to do it. I mean, I've already done it. So it's 847 divided by 3600. 847 divided by 3600 turns out to be 0.23527 repeating. Now, you can probably just round that and multiply it by 100 to get percentage. So it's like 23.5%. So I have less than a quarter probability of actually catching the bus here, which doesn't bode very well. So how can I improve this probability? Well, I can probably wait longer. If I wait longer than 15 minutes, then this graph, this here, would be shifted. Say I'm willing to wait a ridiculous amount of time, all the way until whenever, then this bound would not exist at all, right? This bound wouldn't exist. So this not good region would disappear. And so then the only thing I would have is 60 squared minus 59 divided by 2 squared. So the only time then is if the bus has already arrived and I missed it. So that would be like the most I could do. So if I do it that way, that would be, let me see. I'm just curious. 60 squared minus 59 squared divided by 2 divided by 3,600. Okay, so in that case, my probability is 51.65%, which is not bad. That's, well, it's a slightly better than half. Okay. So you can't force a bus to wait longer for you. So that will be, so about 51%, 51.65% would be the best I could ever do if I'm willing to wait for however long it takes. Okay. So, but for this particular scenario, 23.5%. Hopefully this was clear. This is a great example of geometric probability work. So, all right. Talk to you guys next time.